Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Alif Najmi and I am presenting Polymer Blends and Composites. I'm from section A. So this is the overview for my slide. You can see there is definition, type of polymer blends, polymer composite, type of reinforcement, stability and phase behavior, compatibilism strategies, fabrication and processing method, properties and characterization, application, challenge and future trend, case study, which is toughening a blend, and reference list. So this is the definition part, which polymer blends means combination of two or more polymer physically mixed without chemical reaction. Polymer composite consists of polymer matrix reinforced by filler, fibers, and particles. So the table below differentiates between blends and composite, which in terms of components, blends is multiple polymers only, while composite polymer matrix plus non-polymer reinforcement. For mixing, blends physical often phase separated, while composite embedded reinforcement in matrix. The goals of each blend and composite is different too, which is blends is supposedly for property synergy from polymers, while composite enhance mechanics via fillers. There are three types of polymer blends. The first one is miscible, or we can call it homogeneous. Miscible is single-phase molecular mixing with one gas transition temperature. For example, polyphenylene oxide, polystyrene, like Norway. The second one is immiscible, or we can call it heterogeneous. It means phase separated with multiple Pg values. For example, polypropylene and polystyrene. The third one is compatible, which means immiscible but with strong interfacial interaction for uniform macro properties. Next is polymer composites, types of reinforcement. The first one is short fibers or continuous fibers. These enhance tensile strength and stiffness via alignment in matrix. For example, glass, carbon, and aramide. The second one is particulate fillers, which improves wear resistance and isotropy through uniform dispersion. For instance, clays, silica, and minerals. The third one is hybrid composite and nanocomposite, which combine reinforcement for spurial multifunctionality such as conductivity and lightness. For example, CNT and graphene. For the next slide, it is miscibility and phase behavior. For the first one, thermodynamics, interaction parameter, and Gibbs free energy. The Torrey-Huygens interaction parameter quantifies the interaction energy between polymer segments. It affects the Gibbs free energy of mixing, governing whether polymers are miscible. A negative or low interaction parameter favors miscibility, while higher interaction parameter leads to phase separation. The second one is morphology, droplet matrix, continuous, and lamellar. This describes typical phase structures in immiscible or partially immiscible blends, influencing material properties. Droplet matrix morphology has dispersed, minor phase droplets. Co-continuous means interconnected phases, and lamella indicates layer arrangement. The last one is effect on mechanical and thermal properties. Leachability and phase morphology impact properties like toughness, stiffness, glass transition, temperature, and thermal stability. For example, phase-separated blend may have enhanced toughness, but lower uniformity compared to miscible blends. Next is compatibilization strategies. The first one is use of block or graph copolymers as compatibilizers. Block or graph copolymers such as AB type with A soluble in one phase and B in the other locate at the interface, acting as bridges to lower interfacial tension and stabilize dispersed phases, improving toughness in blends like PP and PS. The second one is reactive compatibilization, or we can call it in situ grafting. This involves melt bending with reactive goods, such as maleic anhydride on TPGMA or HEDS-GMA, that form graph copolymers in situ via interfacial reaction, enhancing adhesion without pre-made additive, which is common for industrial polyolefin blends. The third one is physical compatibilizers and coupling agents. Non-reactive additives like thermoplastic elastomer, EPD and SBS, or silent coupling agents physically reduce domain size and improve dispersion through polarity matching or absorption, often used for economic compatibilization in composites. And for the next slide is fabrication and processing method. The first one is melt bending and extrusion. This is the most widely used industrial method where polymers are heated to the melt state and mixed using extruders or internal mixers. This method facilitates large-scale production, good dispersion, and is compatible with injection molding. The second one is solution blending. Polymers are dissolved in a common solver, mixed, and then the solvent is evaporated or precipitated. This method provides finer mixing for some blends, but is less commonly industrially due to solvent recovery issues and environmental concerns. The third one is in situ polymerization and layup for composites. In situ polymerization forms the polymer matrix around fillers or reinforcement during polymerization for improved bonding and morphology control. Layup involves manually arranging reinforcements such as fiber mats, followed by resin impregnation and curing, which is common in composite manufacturing. For properties and characterization part, the first one is mechanical properties and techniques, which tensile testing measures stress strain behavior for modulus, strength, and elongation. Impact test assess toughness, like Izod Sharpie. DNA evaluates viscoelasticity via storage and loss modulus tan delta over temperature and frequency. This reveals synergy or phase separation effects in blends. The second one is thermal properties and techniques. BSc identifies glass transition, melting and crystallization for miscibility. TGA quantifies thermal stability, decomposition temperatures, and residue for filler content in composite. Multiple TG pits confirm immiscibility. And lastly, microscopy for morphology. SEM visualize phase domain, fracture and dispersion at micron scale. EM provides nanoscale resolution of interface, lamella, or nanoparticles. This is essential for linking structure to properties like toughness. This is application for polymer blends and composites. For traditional application, they are in automotive, aerospace, consumer goods, and biomedical. And for sustainable blends and biocomposites, there are PLA, starch, and natural fibers. Despite all of development in this, there are challenges and future trends. The first one is recycling and end-of-life challenges. Heterogeneous blends and composite resist separation, for example thermoset matrices with fiber, which leads to downcycling or landfill issues. Solution includes mechanical grinding, pyrolysis, and chemical solubilisis for fiber recovery. The second one is sustainability and biogas design. This shift to recyclable designs and biomaterials such as PLA or natural fiber composite, which reduce fossil fuel use, driven by regulation and carbon footprint goals in automotive and aerospace. The third one is advanced compatibilizers and predictive modeling, which next-gen copolymer and AI/ML models predict blend morphology and properties from composition, enabling precise processing and upcycling of recycled systems. There is a case study of toughening a blend, which result in our discovery. The first one is small compatibilizer addition improve toughness. For example, in the literature, in PLA and Pa12 blends, adding 1 to 5% PLA-GMA compatibilizer boosts impact strength from 28 kJ per meter squared, which is uncompatibilizer, to over 40 kJ per meter squared, WT reaching 290% innovation via final morphology and interfacial stitching. Similar gain is seen in PVDF and PLLA with SAD copolymer, raising fracture toughness to 3.2 megapascal square root meter. For the design approach, control interfacial addition via copolymer forming bridges and morphology, which reduce domain size lower than 1 micrometer during melt processing to enable stress transfer, cavitation, and shear yielding for dramatic toughness gain without sacrificing stiffness. This is list of reference that I use for my presentation. I hope you enjoy and learn something from my presentation. Thank you and goodbye.